Equations of lines. The line L in two-space that passes through the point P0 with coordinates x0 and y0 and is parallel to the non-zero vector v with components a and b has parametric equations x equals x0 plus at, y equals y0 plus bt. Let's look at a picture of the plane with a point x0, y0 plotted there. And let's draw a vector AB in standard position. Let's move that vector so that its initial point is the point x0, y0. So to get to the terminal point, we move right A and up B to get to the point x0 plus A, y0 plus B. Notice that the point x0, y0 corresponds to a t-value of 0, right? If we plug in a 0 for t in those parametric equations, we get x equals x0 and y equals y0. And the point x0 plus a, y0 plus b corresponds to a t-value of 1, right? If we substitute t equals 1 into those parametric equations, we wind up with that point. So it seems like the line passing through those 2 points has those parametric equations. Similarly, we can do something like this in 3-space. In 3-space, the line L that passes through the point P0 with coordinates x0, y0, z0 and is parallel to the non-zero vector v with components a, b, and c has parametric equations x equals x0 plus at, y equals y0 plus bt, z equals z0 plus ct. Okay, very similar to what we have in 2-space, except we have one extra equation because we have one extra coordinate of the point and one extra component for the vector. Now, instead of writing 2 or 3 parametric equations, we can instead write a single vector equation. A vector equation has the form r equals r0 plus tv, where in 3-space, r would be the vector xyz, r0 would be the vector x0, y0, z0, and v would be the vector abc. Now, the parametric equations and the vector equation are nearly identical. Let's just verify that the vector equation leads to the same parametric equations in 3-space. So just doing direct substitution, replacing r by the vector xyz, r0 by x0, y0, z0, and v by the vector abc, we have this equation. Now we could use the definition of scalar multiplication to bring the t inside of the vector abc, right? T times abc is the vector ta, tb, tc. And now we can use the definition of addition to add those 2 vectors on the right to get x0 plus ta, y0 plus tb, z0 plus tc. And now remember that 2 vectors are equal if and only if they're equal component by component. So this equation is equivalent to the 3 equations, x equals x0 plus ta, y equals y0 plus tb, and z equals z0 plus tc, which is basically the same as the 3 parametric equations we have. Ta and at are, of course, the same thing because multiplication of real numbers is commutative. Same thing goes for tb and bt and tc and ct. Sometimes we might also want to write symmetric equations for our line. We can get the symmetric equations by solving each of the parametric equations for t. So for example, looking in 3-space at the equation x equals x0 plus at, if we subtract x0 from each side and divide by a, we get x minus x0 over a is equal to t. Similarly, y minus y0 over b is equal to t, and z minus z0 over c is equal to t. Since all 3 of those expressions are equal to t, they must all be equal to each other. And that gives us these symmetric equations in 3-space. The symmetric equations in 2-space are the same, except there's one less equation, right? We would just delete that z minus z0 over c. Okay, now it's time to try some examples. Now's a great time to pause the video, try these examples yourself, and then resume the video to check your answers against mine. Okay, let's look at the first one. Find parametric equations, symmetric equations, and the vector equation for the line L passing through 2, 3, and parallel to the vector V with components -2 and 4. We can just write the answer down very easily. The parametric equations have the form x equals 2 minus 2t, y equals 3 plus 4t. Notice that the point 2, 3 appear in the form x equals 2 and y equals 3. And for the vector, those are the coefficients of t. So x equals the x coordinate of the point, which is 2, plus the x component of the vector, which is -2 times t. Y equals the y coordinate of the point, which is 3, plus the y component of the vector, which is 4 times t. Okay, the vector equation is xy equals the vector 2, 3 plus t times the vector -2, 4. Notice we could get this from the parametric equations, or we could get it directly just by looking at the original information. The point 2, 3 turns into the vector 2, 3, and the vector -2, 4 is being multiplied by the scalar t. And now we can get the symmetric equations by solving each of the parametric equations for t. X minus 2 over -2 is equal to y minus 3 over 4. Okay, next let's do the same thing for the line L passing through the point 2, -1, 4 and parallel to the vector v equals 3, -2, 1. The idea is the same. The parametric equations are x equals 2 plus 3t, y equals -1 minus 2t, z equals 4 plus t. The vector equation is the vector xyz equals vector 2, -1, 4 plus t times the vector 3, -2, 1. And once again, we get the symmetric equations by solving each of the parametric equations for t, and we get x minus 2 over 3 equals y plus 1 over -2 equals z minus 4 over 1. Okay, and now let's find the equations of the line passing through the points 2, -1, 3 and 5, 6, -3. This time we're given 2 points instead of a point and a parallel vector, so we need to find a vector to which this line is parallel. The best way to do this is to take each coordinate of the second point and subtract each coordinate of the first point. So 5 minus 2 is 3, 6 minus -1 is 6 plus 1, which is 7, and -3 minus 3 is -6. And that gives us a vector to which the line is parallel. Let's use the first point together with that vector, and then we can write the parametric equations. X equals 2 plus 3t, y equals -1 plus 7t, z equals 3 minus 6t. The vector equation is then vector xyz equals vector 2, -1, 3 plus t times vector 3, 7, -6. And as usual, we can solve each of the parametric equations for t to get the symmetric equations. X minus 2 over 3 equals y plus 1 over 7 equals z minus 3 over -6. Okay, now I just want to adjust that question slightly. And instead of finding parametric equations for a line, let's find parametric equations for the line segment with endpoints 2, -1, 3 and 5, 6, -3. Now, if we follow the exact procedure that we just did for finding the parametric equations of the line, then we get a particularly nice parametrization of the line segment, right? So we're going to once again find v by subtracting coordinate by coordinate, the second one minus the first one. 5 minus 2 is 3, 6 minus -1 is 7, -3 minus 3 is -6, and use the first point to write the parametric equations as we did before. X is 2 plus 3t, y is -1 plus 7t, z equals 3 minus 6t. And when we do it this way, t will always go between 0 and 1. Notice if we plug a 0 in for t into those parametric equations, we get x equals 2, y equals -1, z equals 3, which is the first point. And if we plug a 1 in for t in those parametric equations, we get x equals 5, y equals 6, z equals -3, which is the second point. So if you follow this exact procedure for writing your parametric equations, you could always let t run between 0 and 1. Note that parametric equations are not unique. There are infinitely many ways to parametrize a line, but this particular parametrization is nice and easy, so I always like to do it this way. Okay, last question. Determine if the following lines are parallel or intersect. So we have two lines. L1 is x equals 1 plus 4t, y equals 5 minus 4t, z equals -1 plus 5t. L2 is x equals 2 plus 8t, y equals 4 minus 3t, z equals 5 plus t. First, let's check if they're parallel. To see if two lines are parallel, we just need to check if the corresponding vectors that define them are parallel. So these two lines are not parallel because the vector 4, -4, 5 is not parallel to the vector 8, -3, 1. Right? To get from 4 to 8, you multiply by 2, but to get from -4 to -3, you do not multiply by 2. So these vectors are not scalar multiples of each other. Another way to check this is to divide 8 by 4 to get 2, and then -3 by -4, and you don't get 2. So once again, they are not parallel. Do they intersect? Well, to see if the two lines intersect, we're going to set the x's equal to each other, the y's equal to each other, and the z's equal to each other. But we do need to be careful about one thing. It would be incorrect to set 1 plus 4t equal to 2 plus 8t, and so on for y and z, because then we're not just finding if the lines intersect, we're finding something much more specific. We're finding if they intersect at the same parameter value. The thing is that the two lines could hit the same point, but with different parameter values. For example, one line could hit the point 0, 0, 0 with a parameter value of, let's say, t equals 3, and the other one might hit 0, 0, 0 when the parameter value is t equals 17. If we just set these equal to each other as is, we would miss the fact that those two lines intersected at that point. So what we need to do is we need to change the name of one of the parameters. And what I'll do is I'll leave t for line 1, but I'll change the name of the parameter for line 2 to u to make sure we don't make that mistake. So we set 1 plus 4t equal to 2 plus 8u, 5 minus 4t equal to 4 minus 3u, and -1 plus 5t equal to 5 plus u. So we need to solve this system of equations for t and u. There are lots of ways to do this. I'm going to look for any shortcuts, and I see that if I add the first two equations, the t's on the left will go away because 4t and -4t will cancel. So we have 1 plus 5 is 6. As I said, the t's go away. 2 plus 4 is 6, and 8u minus 3u is 5u. So subtracting the 6's and then dividing by 5 gives us that u is equal to 0. We could then plug u equals 0 into either of the two equations that we just used to get that t is 1/4. For example, if we use the first equation, then we get 1 plus 4t equals 2, subtract 1, and we get 4t equals 1, divide by 4 to get t equals 1/4. Now we need to check if this u and t value work in the third equation. So we're going to replace t by 1/4 and u by 0 in the third equation. On the left, we get 5/4 minus 4/4, which is 1/4. And on the right, we get 5 plus 0, which is 5. They're not equal. That means the lines do not intersect. Notice this is not a contradiction. In two space or in the plane, any two lines have to either be parallel or intersect. But in three space, that's not true. You can have two lines that are not parallel but fail to intersect because you have a whole extra dimension for them to miss each other in. These lines are called skew lines, right? So what we just found is that lines L1 and L2 are skew.